All right, today's problem, we are looking at kth smallest integer in BST. Yeah, another tree problem. Again, we've moved on to binary search trees here, so they are ordered. This is actually one of the first times that well, no, I was going to say there might be a naive solution that we can touch on today. We haven't really been, is it echoey? Is it like, can you hear me though? Okay. Let me know if it becomes so echoey as to result in you not being able to understand me. Okay. Yeah, we haven't really been doing naive solutions here. We'll probably, actually, now that I'm thinking about it, not do that again today, but we will go over two ways to handle this. One that is much more intuitive or easier to kind of handle, and then we'll go over a couple of optimizations. Mostly for space, actually, this time. But yeah, let's read the prompt, and then we'll do a little diagramming, and then we'll hit the code. So given the root of a binary search tree and an integer k, we want to return the kth smallest value, one indexed here that is in the tree. And we've already talked about this before, but just for a little review, for a binary search tree, or to have a binary search tree, we have to follow these conditions. The left subtree of every node will contain only nodes with keys less than that node's key. The right subtree of every node contains only nodes with keys greater than that node's key. And then the left and right subtrees are also themselves binary search trees. So for any node, if you go left, you will always encounter things smaller than the node. And if you go right, you will always encounter things bigger than that node. Okay, so yeah, when you can see these, and they're small examples, pretty straightforward. So for example, this binary search tree, we want the first smallest, or just the smallest element, which if you think about the total elements here, it's 1 and then 2 and then 3, and the smallest one is 1, right? Okay, on the other hand, this tree here, we've got 4 nodes, 2, 3, 4, and 5, and we want the fourth smallest, which gives us 5. Okay, and let me just point something out while we've got the examples on screen. You'll notice that the way that we collected those, if we wanted to think about all the nodes, was to go left, and then self, and then right, which makes sense because the small stuff is on the left, the big stuff is on the right. And in fact, when we added stuff, a new layer here, we just went all the way left, and then we combed our way upward. But no matter what, we have to get everything in the left subtree, and then the root node, and then everything in the right subtree, if we want things to be in order from smallest to largest, right? We'll do a more complex example in a diagram in a sec, but that's the core idea. And then there's just some constraints. K will be between 1 and the number of nodes in the tree, and there will be no more than 1,000 nodes. So this just guarantees that we're not going to have a K value that is higher than all the nodes in the tree or less than 1. So we'll always have something that is reasonable for the tree, and then the values themselves will be between a 0 and 1,000. We're not going to manipulate those or really even, we'll just do comparisons with them. So this is just guaranteeing we're not going to get something weird with integer overflow or anything like that. Okay, so that's the problem. I'm going to diagram a slightly more, in fact, we might have a better tree already. Yeah, we'll just use this tree from yesterday. And let's do a little bit of examination. So we'll pick a value here. So let's say this is our binary. Oh, actually, I forgot we chose one that wasn't working yesterday. So let's move this over here. Put this right here. Okay, so maybe this is our binary search tree. And let's choose a K value that is... Wait, hold on. No, a few things aren't working here, huh? Oh, no, we're good. Okay, yeah. Let's choose K equals 1, 2, 3. Maybe we'll choose K equals 4 here. Okay, so again, the general property that we're really going to rely on here is the fact that if we traverse the whole left subtree, we get all of the nodes in that subtree that are smaller than the root, right? So for any of these nodes, actually, what we could do is just say, hey, before you process the current node, go as far left as you can, and when you can't go any further left, begin to like count the nodes, or that's where you can find the next smallest node, is kind of the idea. So for example, when we start from the root here to find the smallest element in the tree, which we've done before actually, we're just going to go left as much as we can. And as soon as we hit a none node, we go, well, there's nothing here. Let me go back. And the first time that happens, that's our smallest node, right? So this finds us the smallest in the tree, which is 3. And then from that node, we can go right. Well, I kind of wish we had, you know what, let me actually put a node there. Sorry, I'm gonna I wish I had a better example prepared, but I don't, so I'm gonna change this to 5, and I'm going to make this have a child of 1, just so that there's like something more interesting happening there. Okay, so we would go left as far as we can. Once we run out of the ability to go left, we'll backtrack. So there's nothing over here, right? There's nothing smaller. We begin to now handle this node, and it tells us that the smallest node in the tree is 1. Okay. Now, what do we do from here? Well, we backtracked by 1 level, so if there was anything to the right, that would be smaller than 3, right, but bigger than 1. So the next smallest node is somewhere over here, but since there's nothing there, again, we backtrack. So now we've handled the left subtree, the node, the right subtree, and we can kind of wrap back up to here. Right? Speaking of which, since we've handled the whole left subtree on this one now, we can say, hey, let's go ahead and add 3. That's our next smallest value. Okay, and now that we've handled 3, well, actually, I'm going to say we'll wrap back up to 3. Now that we've handled 3, we can start exploring the right subtree. Okay, but again, before we handle this node, we got to go left as far as we can. And once we run out of the ability to go left, that tells us where the next smallest node is. Okay. And again, now that we've handled this node, we should handle its right subtree, and so on and so forth. So we try and go down, there's nothing there. I kind of wish I had done these in different colors, actually. I'm not going to say my OCD, but my detail-orientedness is going to kill me if I don't replace this. It's more like we wrap back up here, and then 3 is like the next node that we process. Okay, and then we begin to go down here. So each of these like separate colors is like what we have to do until we find the next smallest node, so to speak. Okay, so then we find 4. There's our next guy. Okay, now that we've done that, we can wrap back up here. Again, we've handled the whole left subtree, so now we can add 5. And now that we've added 5, we can handle this subtree. And that puts in 6. And you'll notice this is one way we can optimize. If we have some way to detect when we've hit the 5th node in order, we can stop, right? Because we don't need anything bigger. We just wanted the 5th smallest, and we've just found it, right? Now, assuming we didn't think about that optimization, then we would just keep going. We would say, hey, I need to go ahead and look on the right subtree now. Well, there's nothing there. So we'll now unfold all the way up here. And since we figured out the entire left subtree, we can now start going right. Now again, before we process 9, we're going to go left. Well, there's nothing there, so we wrap back up, and that tells us that 9 is the next smallest node in the tree. So this is basically just collecting the nodes in order from smallest to largest. Again, the naive way would just be to collect all the nodes. So now we go here. We get 10. And then finally, the very last thing that we do is we check the right subtree. There's nothing there. And so this wraps all the way back up to the top, and we know that we're done. So yeah, basically if you follow these arrows in rainbow order, you will traverse the whole tree from smallest to largest. Again, we call this an in-order traversal because we handle the whole left subtree before handling the self node, and then we handle the self node, and then we move on to the entire right subtree. So if we follow this process, we always go from smallest node to largest node. If we do that for the whole tree, then all we got to do is now, if we've got these in a list, for example, go to index k minus 1. Oh, sorry. K 0, 1, 2, 3, 4, 5. K minus 1 is over here, and that's our answer. Okay, now again, we would like to not have to do the whole tree because, for example, like what if k is 1? We don't want to traverse the whole tree only to find out we only need the first node, right? So a smarter way to do this, and we'll do both of these in code, would be to check the length of the list that we're generating, and once we hit the length that we want, we just return the last node. So that would be nicer if we can do that, and then we'll talk about even one last way that we can optimize this. Now, in terms of time complexity, this is, I think, as good as we can get, and it's unfortunately roughly O of n, which makes you think, that means we got to look at every node in the tree, which is true. It is O of n. In the worst case, we have to look at every node in the tree, but we are going to provide an early exit once we hit the node that we're looking for. In terms of space complexity, in the worst case, again, we have to store all of these nodes consecutively. There is a way that we're going to optimize that later, but that's O of n currently, and we're going to try and get that down to O of 1 if possible. All right. Let's give this a shot. Let me know if y'all have any questions on the algorithm. Hopefully this diagram, give it a screenshot if you're hoping to explore it more, but hopefully this diagram explains a little bit about what we're trying to do, and we'll translate this into code right now. Okay. So the first thing I'm going to do here actually is I'm going to define, I always forget like how, so we need a list. We need that list to kind of exist separately from the function. Let me think about this. What we could do, I always forget, like, NeetCode has weird stuff about kind of the lifetime, so to speak, of these lists. I think what we can do here is we can say, like, node list equals empty list. Oh, we will talk about the O of 1 optimization later on. We're going to do the O of n space solution right now, just to be clear. So this will be O of n time complexity and O of n space complexity. So we'll start with an empty node list because there's no nodes, right? I'm going to define a helper function here, just so we don't keep calling this and like getting a new empty list. We want that list to kind of persist between the recursive calls. So I'll say kth smallest helper, and this one we just need to pass it a root because it already has access to k from out here. And in fact, maybe I won't call it root because I don't want like collisions there. We'll call it like current, for example. Okay, so this is the thing we're going to actually recurse with, and we're going to have to call it over here. So I'm going to write some explanation here. What I'm thinking about is we have to populate this list, and at the end we'll return the last thing in the list because we're going to stop. Well, which one do we want to do first? Let me think about this. We'll start this by getting all of the nodes, and then we'll modify it to stop when we hit the number of nodes that we need. And then we'll modify it to have O of 1 space. Okay, so those will be our 3 steps here. So if we're going to collect all of the nodes, then I'm not even going to call this kth smallest helper. I'll call it populate node list, or like get next smallest is kind of the way that this works, right? We're trying to say like, hey, if I can just get the next smallest one, then I can add it onto the list, right? Although, ooh, yeah, it's a little tough because we don't really want to call that here. So yeah, really, I guess the name of the function here is like populate node list. Really, it's just like a depth first search. I don't know. It doesn't really matter what we call it. The point is that what this is going to do is it's going to populate this list, and then at the end, we can just return node list at index k minus 1. Okay, and again, we're gonna optimize this in a sec, but this is fundamentally what we want to do. Okay, so how do we do this? Again, we need to do an in-order traversal, which means handle the left subtree and then handle myself and then handle the right subtree, which guarantees that we're always going to go in order from smaller to larger. Okay, so we'll go ahead and populate node list. So this is, we'll add like a base case, we'll add stuff like that, but what we, at the core of what we need to do is populate the node list with current.left, and then add node list, or add the current node to the node list. And then do the same thing with the right subtree. Now, we have our pick of either storing the nodes themselves or storing the values. We'll go ahead and do the value, and that way we can just return the entry instead of needing to like get the value at the end. It doesn't really matter. They're sort of equivalent. I don't think the space difference between like storing nodes and storing integers is vast enough for us to really care about that. So we'll do this, and then our base case is if we hit a none node, so if not current, we can just return. There's nothing to add. We don't need to worry about it, right? Okay, and I think that's it actually, which is kind of crazy. Let's see, am I forgetting something? Was that too easy? Am I crazy? Oh, what did I do wrong here? Left, root.val, populate node list. Oh, hold on. If we want the fifth smallest, okay, hold on. 3 nodes. We want the first smallest. It should be k-1, shouldn't it? Awkward. Ooh, this is embarrassing. I said like this was going to be so easy, and then I really messed it up. What did I mess up, you guys? Oh, not root.val, current.val. My bad. I literally said, let's not have any naming collisions, and then I created the naming collision. Anyways, so yes, this works just fine. Let's just make sure it works for the cases in general, and we're good. Okay, so again, again, what this is going to do is get all of the nodes in the list in order, and then we're just going to pick the one that we want. But again, we would like to not have to do that, especially if it's like a very early one. Like we just want to get to the one we want and then stop. So how can we do that? We can say there's another base case here, and the other base case is if the length of node list is k, then we're done. We don't need to keep going, right? I think, is this where we want to put it? I think this is where we want to put it. We could also put it like right here. I don't think it matters, but so we can do this. And then this should still work actually. Let's just find out. Yeah, so this still works, but another way to phrase this to make it more clear in terms of like the logic of the algorithm is we could say, oh, well, we just got to the very end. We got the last node that we needed. Let's go ahead and return the last, oh, you know what? That's because I need to put it right here. So we just got the very last node that we needed. Go ahead and return. I think this should work now. What? Oh, just kidding. Sorry. No, we still need k-1 because it might not be the last node. Although, shouldn't this have stopped right here? Uh-oh. Uh-oh. Wow, I was not expecting that to happen. So what I thought was going to happen here is we were going to stop when we reached the appropriate length and then just return. Now, why didn't we do that is the question. So like we should have added 2, right? Let's take a look here. I'm going to put this back here because it is, I think logically this is where we want to stop. Like we add a node and then we go, ooh, we're good. But now that I think about it, this is just going to end like a single recursive call, right? We kind of want to say like just stop all recursion at this point. So how could we say like stop recurring? Let me think about this. So we want to stop all recursion once we hit the condition, right? Well, we can't use break because we actually have recursive layers. It's not a while loop, it's not a for loop. I've definitely done this before, and I'm totally blanking on how to actually do it. We basically just need to like check condition before we continue to recurse. I guess we can actually put it here. Here? It's like do the left, let me think about this. Do the left subtree, and if the length of handle the left subtree. No, I don't feel like this is actually a good way to handle it. Ooh, I feel silly. I feel like this should be straightforward, but my brain is not braining on how to actually break the recursion. Basically, we need some way of saying, like, stop once the list, like, stop entirely once the list is the right. Yeah, I am kind of hungry and kind of tired, and I just took an exam, which is not helping my brain, but that's okay. We can figure this out. So we have the node list. We begin to recurse, right? We go down the left subtree first. This is one of our base cases. I guess what we could do is we could just add like a flag. But then I guess the flag is just checking the node list anyways. So you know what? We could just put it at the end of all of these, huh? So before you do any recursion, check, basically. I feel like there's got to be a better way to do this. But let's see if this works. Yeah, it does, but I kind of hate that. I feel like there's got to be a better way to do that. This is basically just saying, hey, before you start doing other things, before you start continuing to recurse, just check if we have all the nodes we need. And if we do, you don't need to make a recursive call. Just let it die, basically. So this works. There's almost definitely a more elegant way to do that, though. I just can't seem to think of it. I guess if we put it here, no, yeah. I'm gonna think on that more. For now, I want to talk about the O of 1 space optimization. I'm gonna continue to think about this because it's kind of bugging me. I feel like there's got to be a better way to handle this, and we might look at some of my past submissions because I feel like I've handled it before. But here's the other thing we can do. Right now what we're doing is we're adding all of these nodes to a list, but the thing is we don't care about most of them, right? Instead of tracking all of these nodes and storing them and duplicating them, or at least duplicating their pointers, what we could do is just keep a counter, and just once that counter hits the appropriate size, we stop, right? Now, one of the weird things about this is that Python, when we pass primitives like integers, we can't, wait, actually, I haven't thought about this before. What I was gonna say is one workaround for this is, in fact, I think we'll start this from scratch here, mostly. We can say something like node counter equals a list with 0 in it. And this lets us kind of have a persistent integer that we can just modify at will. If we just made it this, Oh, actually, hold on. This might be okay. Ooh, but this is where it gets weird. Let me explain myself real quick. If we handle it this way, where we just keep track of a counter instead of a bunch of pointers to nodes, like in a list, in that case, when we hit the node that we want, we have to pass it all the way back up the tree, right? So, well, okay, alternatively, we could just say res equals none to start with. And then when we find the node that we want, we can just put it in here, right? So if not recurrent, return if node counter equals k, return oh god. And then I'm going to change these because we're no longer populating a node list. We'll say like traverse. And then here we call it on the root. And then here we'll return res.val. Okay, and then in here, these also become node counter. Okay, and then at the moment that we hit this, ooh, so this part actually, when we get to the current node, we'll say node counter plus equals 1. And then if node counter equals k, then res equals current, and then we return. Okay, so this way we don't need to store all the nodes. Again, I'm like 95% sure there is a more elegant way to handle this, which is so sad because I'm supposed to be teaching it, but that's fine. Me, when I was literally thinking yesterday, I don't need to review these before we do them. I have enough knowledge, and then I wish I had reviewed this one. Anyways, in short, we don't store all the nodes now. We just, when we hit the node that we want, we set the result to that node, and that's the only one we have to store, right? Now we have the node stored, and we can just return the value. I think this should work. Let's give it a run. Oh, I did it again, not root. Oh, wait, what? Node counter? Oh. I think in order to do this... Oh, interesting. I think I just have to say non-local right here. And it'll let me access that. And then I think also non-local res. This just says, hey, by the way, the scope of this variable is somewhere else. Oh. Now what happened here? Name, oh, what did I do? Whoop, don't need that. Oh, I'm full of mistakes today. Great, and she works. Okay, so the optimization here is let's not store all the nodes. Let's just keep a count of how many nodes we've seen so far. And when we get where we need to go, or when we get to the one we need to get to, we stop, we store it somewhere, and we're done, right? There's probably, again, a more elegant way to do this. I think what we can do is we can pass along an argument instead that tells us like what node we are in the tree, if that makes sense. Let me think about this though. So here's what I was thinking was we could have something like current and rank. The problem is, what do I tell the root its rank is at the beginning? It actually depends on like the recursion that happens, right? Like we don't know what the rank is until we've completed the left subtree. which is kind of fine. This just means we won't... Ooh. I feel like there's got to be a way to do this. Let me think about this. We can't give it a rank to begin with, but we will get returned a rank from the left subtree, right? I still don't feel like there's a good way to do that, though. Well, yeah, so basically we can just do this. This is going to return the rank of the root, but that's fine. We're just going to throw it away anyways. So this is kind of like traverse until kth node is maybe the name of that we should use here. So this way we don't need an external node counter, and we don't need a rank argument. I'm going to keep this just because it seems to be the best way to like track what the node is when we get there. Okay. Now actually, I bet we could just return this. Sorry, let me close this window. I want more space. Okay, traverse until kth node, current node. We're gonna do this starting from the root. And then, well, okay, yeah. I was gonna say, yeah, actually I'm gonna keep the res part of this only because a bunch of these nodes like are not gonna know what the kth node is, right? Initially what I was thinking was, oh, go ahead and have it pass back a tuple that has like the rank of the current node and the kth node. But that's not nice because most of these don't know what the kth node is, right? They don't find out until we get to the kth node. So instead, we'll keep the non-local res thing. We don't need the counter anymore because we can just, basically what this function will return is like the rank. Yeah, it returns the rank. I'll leave this as a comment. Return the rank of the node. And by rank, I just mean like its placement in the tree. Okay. So still, if we hit a none node, there's nothing to do. We just return. Ooh. So the rank of the node is going to be the size of the left subtree plus 1, right? So for example, in this tree, like the rank of 7 is 6. The rank of the root is 6 because there's 1, 2, 3, 4, 5 nodes over here, and then my rank is 1 more than that. So let me destroy all this real quick. Okay. I'll say rank equals traverse until kth node current dot left plus 1. Okay. Now this handles the left subtree, and then it also gives us the rank of the current node. Ooh. Does this affect the base case? It might. The base case is that we hit a none node, in which case the rank does not change, right? Yeah, I guess now that I think about it, the only way to do this would be able, so like when you go down the right subtree, for those guys to know their rank, it would have to be, ooh, yeah, there's too much to keep track of here. I'm not liking this very much. Okay, well, this was a fun exercise. I don't know if I'm going to get through this part or if there is a way to do it. I'm curious. This is the first time I've really thought about it. It doesn't really affect anything in terms of like performance, so I'm going to say we shouldn't worry about it too much. So let me back up just so that this ends on a nice note. This is probably where I would stop. Like, this is my final optimization here. I'm going to think a little bit about a better way possibly to do this. Because I feel like, again, there's a better way to handle this recursion or to break out of the recursion if we hit the count that we want. I just cannot seem to think of it right now. Let me like pause for just a moment to see if something comes to me. Yeah, the issue is that we sort of like arbitrarily might be in any one of these sections in a certain part of the tree when we hit the number of nodes that we need. So this isn't too bad. I kind of feel good about like this whole thing right here. It's a little bit not as nice as we'd like, but I think I can accept it. We might not even need this one now that I think about it. Wait. Anyways, wherever my last submission was, this is probably the one that I would stop on that actually worked. Yes, this guy right here. I'm going to think on this a little bit. If you're curious about how this might be optimized or like just made more elegant, I'll try and post a solution in the thread for this problem. But I'm going to say we did pretty darn good. We worked this down to O of n with early exit time complexity, and we also worked it down to O of 1 space complexity, which is quite nice. And I actually am going to take that back. It's O of 1 space complexity in terms of what we actually store as data, and then it's O of log n space complexity for the recursive calls, right? So since we have to recurse potentially all the way to the lowest part of the tree, that's going to be log n space complexity, or if it's really bad and it's just a linked list, that would also just be O of n space complexity. So the recursion is the issue here once we can optimize it down to just storing a counter. But this is pretty darn good. This is very close to being the optimal solution. It's just not super elegant. And that's that. I'm going to call it there unless anybody has questions. And yeah, keep an eye out on the thread if you are curious about how we might refactor this code to make it a little bit more elegant. But we'll call it there, and I will see you guys tomorrow night.